Let us see the working of thermal camera and Luxmeter. This will be presented by me, Harsh Walavalkar, and my teammate Aaryan Waghmare.
The infrared radiation lies between the visible and microwave portion of the electromagnetic spectrum. The difference between infrared and visible light is the wavelength. Infrared has a longer wavelength than what we can see with our naked eyes. We can demonstrate this in another way too, using Max Planck's law of radiation. It is an equation which provides a curve which illustrates that the warmer a body is, its emission at each wavelength, and the shorter the wavelength at each emission peak. It seems complicated, but it isn't. This is the curve at 37 degrees Celsius, the normal body temperature of a human being. Maximum radiation is emitted about 9.3 micrometer, and we can only see this radiation with the infrared camera. If the temperature increased to 300 degrees Celsius, the peak of the radiation moves about 5 micrometer. We still need an infrared camera to see this. Suppose the temperature rises to 5500 degrees Celsius, that is the temperature of the sun. Then the peak of the radiation is zero point 0.5 micrometers, and this is right on the part of the spectrum that we can see with our eyes. The primary source of infrared radiation is heat or thermal radiation. A thermal camera, also known as infrared camera or thermographic camera, operates based on the principle of detecting and capturing infrared radiations emitted by objects. Unlike traditional cameras that captures visible light, thermal camera detects the heat or infrared radiations emitted by the object. Here's a basic overview of how thermal cameras work. First is the infrared detection. All objects with a temperature above absolute zero emits infrared radiation. The amount and type of radiation depends on the temperature of the object. A thermal camera uses a special sensor called as microbolometer to detect infrared radiations. Microbolometers are made of material that changes their electrical resistance in response to temperature variation. The third step is color mapping. Thermal cameras often use color mapping to represent different temperature ranges. The color scale, known as thermal palette, helps visualize temperature variation in the scene. For example, a typical thermal palette uses warmer colors like red and yellow to represent higher temperature, while cooler colors like blue and purple represents lower temperature. Let's talk about the applications of thermal camera. Thermal cameras are invaluable tools with multiple applications across diverse fields. In the realm of security and surveillance, they excel in identifying individuals or objects regardless of lighting condition, effectively detecting them in complete darkness or through obstructive elements like smoke and fog. In industrial settings, these cameras play a critical role in inspection by swiftly detecting heat anomalies within electrical systems, machineries, and other equipment, aiding in proactive maintenance and preventing potential failure. Their utility extends to medical imaging, where they serve in diagnosing ailments by identifying temperature variation within the human body, providing a non invasive means of accurate diagnostics. In firefighting operation, thermal cameras prove indispensable, allowing firefighters to pinpoint hotspots even in challenging environments obscured by smoke, enhancing their ability to navigate through hazardous conditions and combat fire more effectively. Moreover, in search and rescue conditions, these cameras are instrumental in finding individuals in difficult terrains or adverse conditions, aiding rescuers by detecting body heat signature and significantly improving search effort in low visibility situations. The versatile capabilities of thermal cameras across security, industry, medicine, firefighting, and search and rescue underscore their pivotal role in enhancing safety and efficiency across various sectors. Here, we have provided the block diagram of thermal camera to get a better insight of the working principle of thermal camera. In the following videos, you can see how the thermal camera shows temperature around people and different objects.
Thank you, Aaryan, for your explanation. Now, myself, Harsh Walavalkar, will explain you the working of Luxmeter. So, let us see what exactly is a Luxmeter, what is lux, how is lux measured, and levels of lux in different areas. So, what exactly is a lux meter? A lux meter is a light device used for measuring brightness, specifically the intensity with which the brightness appears to the human eye. A lux meter works by using a photocell to capture light. Now let us see what exactly is lux. Lux is the unit of illuminance or luminance per unit area. In the international system of units, it is equals to 1 lumen per square meter. In photometry, this is used as measure of the intensity. Now let us see how is lux level checked. We keep the lux meter in the vicinity of the light. And now let us see some of the standard values of lux in different areas. So in a clear outdoor, the value should be 10,000 lux. Clear day indoor, it should be 1000 lux. Mechanical workshop, it should be 750 lux. Offices, 500 lux. And near equipment, it should be 150 to 200 lux. A lux meter, also known as a light meter, is a device used to measure the intensity of light in lux, that is, lumens per square meter. Lux meter are commonly employed in various applications, including photography, cinematography, environmental monitoring, and industrial setting. Here's an overview how lux meter works. 1. Photodiode or photovoltaic cell. The core components of a lux meter is a light sensitive sensor, typically a photodiode or photovoltaic cell. When exposed to light, the photodiode generates a current or voltage proportional to the intensity of the incident light. Second, calibration. Lux meters are calibrated to measure light according to the sensitivity of the human eye, which is the most sensitive to green light. The sensor response is usually adjusted to mimic the human eye's perception of brightness. Third is the unit conversion. The electrical signal generated by the photodiode is converted into lux, the standard unit of illuminance. Lux is defined as 1 lumen per square meter. Lumen is the measure of total visible light emitted by a source, and lux takes into account the area over which light is distributed. Fourth, display. Lux meters are equipped with a display that shows the measured illuminance in lux. Some devices may also provide additional features as the ability to capture minimum and maximum readings or display the average illuminance over a period. Now let us see the application of lux meters in diverse fields. First is the photography and cinematography, ensuring proper lighting conditions for capturing images or filming. Second, building design, accessing natural and artificial lighting in cultural architecture. Third is the environmental monitoring, measuring light levels in outdoor spaces, greenhouses, or work environment. Last but not the least, safety inspections, verifying adequate lighting in workspaces to ensure safety and compliance with regulations. Here, we have provided the block diagram of lux meter for better understanding. Here, you can see the value of lux under various conditions. In the first video, we can see the value of lux under shadow. In the second, we can see the value of lux under flashlight. Last but not the least, value of lux under sunlight.